take it away.
Thank you for the introduction. So this is a joint work with Rupak, Majumdar, and Marcus Pirron at MPI and Nobuko Yoshida at Imperial College London. So this is some work we started about, in some sense, looking at session types in context of robotic systems. So where, in some sense, the messages not only you want, well, for the robots have communication protocols, but those messages sometimes is to agree what they do next in the physical world. So our running example will be this kind of simple looking example that we have this small robot here that carries an object, and we want the two robots to meet. So they are going to decide sometimes where to meet. They move to this location. Once they have to get close enough so that the object is in reach of the arm, but they don't want to get too close so that we avoid collisions. Then we grab the objects, get back to the normal position, and then acknowledge we are done, and the two robots can part their way. So it looks simple enough. And now the first question we can ask is, I guess most of you would think that there is two robots in this picture. Actually, we have three. So the software is not only the only place where we have reusable components. So in the case of robotic system, well, the arm makes sense on its own, so it's a separate robot that has been built and programmed separately that runs its own code. And the cart also has been built and programmed separately. We just happen to attach them together in this example. So that will be one of the challenges we are facing. Sometimes is this kind of separation of hardware, logical separation of hardware, while still having very strong physical coupling. And in some sense, if we can think of this world, we have these two robots basically sometimes moving around the world, and in that case, the world from the perspective of the arm is given by the position of the cart. So robotic is a very wide field, and here we are going to find a kind of niche or very specific topic that we can address. So first, the question is message passing abstractions, because in some sense we have a physical world that is shared. The motivation is basically come from the robotic operating system, or also called ROS, which, as the name implies, is not an operating system, but a middleware. And at the core of ROS is actually a publish-subscribe system. So in some sense, message passing is oblivious in robotic systems. And at least within academia, ROS is a kind of de facto standard that many people use it because it makes it so much simpler to build and program robots. It's even used for prototyping within industry. So here in this talk, we are going to first, in terms of the robot we look at, is this question of some robot design and build a separate component that we want to, in some sense, attach together, and then we want to have all these components execute some protocol so that it looks like it acts as one robot, like this cart and arm. And also in terms of code, there is a lot of different code in a robot, and here we are going to look mostly at what I would call kind of planning, which is, how do you communicate with the other robot? How do you agree on what to do next? But there is a lot of other code which is more control-oriented, which is once you have agreed on what to do, how you actually do it, following trajectories, this kind of tight feedback loop with sensor and actuator. So this is not the focus of this talk. So let's look maybe at what could the code of this arm look like. So like it has been physically designed separately, the code could be also try to be as generic in some sense, kind of the arm as a plug-in component. So the code says that basically it's a big while loop that waits for messages. And then depending on the messages, for instance, when it tells to grab some object, specific location, it's going to execute what we call a motion primitive, which is just an abstraction of lower level controller that will actually reach from sensor or send message to the actor to execute some action. And when it's done with this action, it's acknowledged back. And another interesting maybe thing to notice is since when you receive messages, you might not know when the message comes. You also, in our model, define a default, in some sense, motion primitive. Like, what do you do with the physical hardware while you are kind of sometimes stuck waiting for a message? But the code has this kind of strong decomposition into what we call motion primitive and communication. So the starting point of this project, maybe which relates to this two keynote talk that we had yesterday and this morning, is sometimes to do verification of those systems. And the first idea, if you want to do verification, is that you have a global specification, you take your implementation, you just build a product and check that it refines. However, this is just computationally way too hard, and I hope the two keynote managed to convince you that we need to be compositional. And that's how we kind of started looking at session type, because in some sense they offer a very nice way to be compositional by default. So we start with a kind of global specification, which is in the multi-party session type-based global type, that then gets projected onto the endpoint. So this basically produces now local specification for what each of the robots in our system needs to be doing. And then the kind of check against the implementation is only against the local specification. So in some sense, we're never building the product of all our different, basically implementation model of our robots, which is kind of very nice and what we, why we started this line of research. So quickly, in the rest of this talk, I will discuss about all these elements of the model. You know, what is the model? What are those global and local types or specifications? How we go from global to local, that's the projections. Once we have those local specifications, how we make sure our process implement those local specifications, and then a little bit about experiment and future work. So the model is, in some sense, a very strong model. So at the level of software, we assume, well, point-to-point communication, which is normal, but we assume communication to be synchronous. Just because, in some sense, communication is a much smaller time scale than the actual physical time it takes for the robot to move around. So we use synchrony as a kind of approximation of that. And similarly, we assume computation to be free. So it's basically standard assumptions in the world of hybrid systems. At the level of the robot, basically each robot has its own kind of physical state. This state can be coupled to the set of other robots. For instance, if we attach the arm on the cart, then the cart might be slower because now it weighs more. So that's kind of affecting its dynamic. And also we have what we call a resource function that, given the set of the robot, tell us, you know, how much space the robot actually needs. So that's, for instance, something we need for checking collision, because, well, our language, in some sense, a program is only well defined where the robot don't collide. When it collides, we just don't know what happened. Yeah, and now to change this state, we'll basically go through this motion primitive, and basically, in the paper, we go into more detail about specification, like pre and post condition invariant. But for this talk, I will really focus on the synchronization aspect, so the communication. And for motion, we'll just assume that motion takes some time. We'll not dig further. So the level of this global specification or global type, here we have a very kind of simple, in some sense, extension of session type, that we have the usual kind of communication or with branching, which means that we have a sender or receiver. And between, for this communication, we have a set of alternative messages that can be sent between the two. And each message can result in its own continuation. And on top of that, basically what we had here was we call this motion. Basically this tuple that for each process says what physical action each of the robot must be doing. And again, we have kind of also recursion, like you would expect. Since our recursion doesn't have argument, basically those specifications are regular languages in some sense over both the messages and the kind of this motion primitives. So here it's very nice because we still have a strong kind of separation of motions and communication. However, now when we are going to go to the level one step closer to the robot, that's where it starts getting a bit more murky and things will start mix somehow. So we'll still recover motion as a separate element. As usual, communication gets split into receiving and sending, which also gets split, the choice gets split accordingly. Whether when you are sending, you have basically internal choice, so you are in charge of picking the message you send, versus when you receive, well, the other, the sender actually choose which message to send and you just have to react to it. But now we have this kind of interesting extension of the external choice where we can somehow react both on messages but also on time. So that's to capture, for instance, this case where we are potentially waiting for a message, we're not sure when the message will come, but we still, you know, need to do something in the meantime, or we need somehow to be able to tell the hardware or the physical robot what to do in that time. And here you can think of this mix of motion, or what we call the default motion with message reception, as in some sense being kind of like a broadcast message, a timeout message. So time is kind of like a message that it broadcasts across all the robot and all the system at the same time. So that's kind of why it appears here. So now let's go back to our example and see how we can express. So the example means a simple example. Even though the things looks quite big, it's actually just a sequence of message and events. There is nothing really fancy. So you first say that we want the arm to be folded, so we send a message, and then the arms fold, and then it's acknowledged. Then we say, the card says to the card, okay, we can meet, so they both move, and so on and so on. So that's the global specification of what we want the system to achieve. Then, for instance, when we look at the arm, what we do is just to get the local specification of the arm, well, we just get rid of everything else. And then we can tidy it up to make it fit the syntax of the local type. And that's very simple at this level, but it's not always possible. So here we have to be a bit careful. Unfortunately, for time reasons, I will not go into all the detail, but to explain it in more detail. But implicitly, if you have this question of taking a global specification, projecting it, and implicitly when you run on the robots, basically these things, you implicitly take a product again. In general, you may add new behavior to your systems. So a geometrical analogy is that if you start with this line, you project on the 2 coordinate, and then you recompose, which is taking the product, you don't end up with what you started. So you added more things. And if we want to do kind of verification, adding more things is usually completely unsound. So that's actually a case that we need to avoid. I'm not going to explain the detail, but I refer to a paper. Actually, not every global specification can be projected, so we have to perform both some check at the level of this global specification that it can be projected, and then the projection itself is a partial function. So not every global spec admit a local implementation. Okay, so now let's go back to, so we projected those specifications, we have our code, and let's see how we can make sure that this indeed implement the type. And first thing that we see that, well, we have all the elements we need, but they are quite not somehow in the right order. In particular, also here we have a loop, and here we have just a sequence. So the type checking itself is not just not so straightforward, and the way we can fix that is actually reducing subtypings. So this is not does not really match this type, but is actually, we'll see, as kind of a subtype of this. So I'm just going to focus on one rule to quickly give you the idea. It looks very nasty at first and big, but we're going to go piece by piece and not that complicated. So here you have the subtype on the left and the supertype on the right. And the first thing we see is that they share common element. In this sense, basically we have a set of messages, and those are shared, so we need to check that for the messages that are shared between the 2 types, well, they agree. On the other hand, the interesting things is that on the supertype, we can actually have more things. So we can think of the supertype being basically the promise in terms of reception of all the message you can receive at that point. So if you have code that can react on a larger set of events, well, the supertype promise that you only receive this subset, so this extra part of the code is allowed to be there. It's just basically dead code at that point in the software. So if we go back with this observation, we go back to our example. So roughly what the subtyping does at a very high level, in that example, we can think of unfolding the loop a few times. And now, basically, we are going to just use the subtyping for each of those actions, so that in some sense, at each of unfolding of the loop, we just pick the message that we want. And basically, that's how, in that case, we can, in some sense, even though the 2 programs looked fairly different, actually, the ARM implement is specification. I'll quickly comment a bit on experiments. So we did a bunch of experiments. Actually, you'll see that the robot looks a bit funny because, well, since we are more PL person, we wanted to understand a bit more about robots, so we built ourselves the robots. Well, I mean, for the ARM, we mostly downloaded the blueprint for the physical part, but we did all the software. And for the 2 cards, actually, we built them pretty much from scratch. And we implemented our small language with our type systems, so it runs on top of the robotic operating systems. We implemented also a verifier, so here there is also this question of motion primitive specification pre and post condition that I briefly mentioned but did not address. So the paper discusses also about all that and how we can deal with that. Yeah. So maybe in summary, so I presented here an extension of synchronous multiparty session type with this motion primitive, which allow us both to get the good property of session type, for instance, as communication safety, the log freedom of the communication, and also talk about the physical world, so that we can apply it on the case of robot. In terms of verification, it's also really good because it's enabled this compositional verification. We have everything available now. There is a lot more in the paper. But now maybe one kind of quick last comment, or I guess why we submitted this as a kind of brave new idea. In some sense, if we go back to the keynote of Ilya yesterday, I completely agree with you that PL has a lot of very nice tools and technology that enable us to understand software and basically proof system and so on, or type system like in this case. And I think there is a lot of application in robotics, but we don't want to sometimes be PL person doing robotics. Or we wanted to start to actually, part of this project, which is much wider, actually reaching out outside of the PL community and see if we can somehow gather interest to people actually building robot or using robot on a daily basis. So, for instance, there is, on those motion primitive, if we want to have this robot to be component that we reuse here and there at something at ICCPS, so it's a cyber-physical, basically it's conference on cyber-physical systems, so it's not, somewhat between PL and robotics, but here we address some question of modular specification. Later this year, we'll have a paper part of this project that will be at a robotics conference itself. So I think in order for this kind of, for instance, application of PL technology to robotic to succeed, we also have to do all this outreach, whether it's brave or foolish, I guess time will tell. And notice that the two are not mutually exclusive. Thank you.
Okay, we have maybe 1 minute for a question, and maybe we can take others in the break. There's one at the back there, yes.
Have you considered, it was an interesting talk, thank you. Have you considered extending the session types to value-dependent session types to give you greater reasoning about the messages that your robots are sending, or not robots sending, but like the formation of your global type?
Sorry, what was the question?
Have you considered extending your notion of session types to value-dependent session types?
Yes, actually already in the paper we briefly talk, because that's true. In some sense it comes with the motions that when you move, for instance, you have this precondition, so you move only if some condition is true. And sometimes you need to communicate something to the other robots, so you want to kind of carry. So in this paper we discuss more, so we extend, so the first part where value become important is in the choice. So here I only showed non-deterministic choice. In the paper we present an extension where we have guarded choice. So when you take a choice, it will tell you something about some value, and then you can also use that. I think in this version we mostly use this guarded choice at the global level, so there is also more check about the motion at the global level. But yeah, we are working on, in some sense, extending the richness of what we can express through messages. So right now there's still a few global checks related to value pre and post condition. Yes, thank you.
Okay, I think I misspoke because we don't have a break. We're moving straight on to the next keynote. Is that correct? So let's thank our speaker once again.